Congratulations! If you saw this episode's title and decided to listen anyway, then you're a true military aviation enthusiast who knows that not every show can be about the latest Gee-Whiz fighter or the making of the recent blockbuster movie. Either that or your podcast player automatically went to the next episode while your hands were tied, but either way, this is the Fighter Pilot Podcast, episode 147. And yes, we're talking about flight control systems this week, including fly-by-wire technology. Now, this isn't the sexiest of stuff, admittedly, but hey, it's important, and you know we're going to have a good time, as always. Let's do it.
Strap in for the Fighter Pilot Podcast, the internet radio show that explores the fascinating world of air combat, the aircraft, the weapon systems, and most importantly, the people. Now, here's your host, retired U.S. Navy fighter pilot, Vincent Aiello.
Hello and welcome to the show. I am your host, Jello, and that's right. This week, we are geeking out a little with our flight test engineer and occasional co-host, Ken Katz, call sign Primetime, who will be along shortly. But first, it's been a little bit. I hope you're doing well, having fun and enjoying your summer up here in the Northern Hemisphere. For those of you who celebrate America's Independence Day, I hope you had a safe and enjoyable holiday. We certainly did. We were a little bit heartbroken while enjoying our town's parade to read about the violence that occurred at a similar parade in Chicago. Man, I don't know, just breakdown in values these days and stuff like that keeps happening. It's really awful. Now, speaking of sad news, just to get all that out of the way, this past week, the NTSB released the preliminary report of Snort Snodgrass's fatal mishap. You might remember that. It was about, I don't know if it's quite a year ago, but the report included a sentence which reads, quote, "Given this information, it is likely that the control lock was installed on the flight control stick during takeoff and impact." And man, that just, I tell you, gives me the shudders, because if it can happen to someone with that much experience, I don't think any aviator is safe. Now, I don't know what happened leading up to his flight, but theoretically there should have been a checklist to prevent that. And so, man, that's just heartbreaking. In happier news, I do want to thank everyone who donated to the F-14 Tomcast. Man, we blew away our goal and will easily make it to next month's finish line with those guys in the black. So that's a good thing. Let's see what else. If you were one of the roughly 200 members of our Facebook group called The Hangar, which was dedicated to aviation model enthusiasts, and if you're wondering where that went, well, I put a note on there and then deleted the group a few days later because it just really wasn't moving the needle and was simply one more thing I had to manage. So in the spirit of spring cleaning, we shut that down. And then regarding last week's intermission episode featuring our friend who's running for office, it's funny. I received, a handful of different kinds of notes, but several from listeners who frankly were disgruntled when they learned what political party Ruckus is affiliated with. And I guess it's just a no-win situation, because about a year ago, I received similar messages when we promoted on this podcast a news channel of the opposite political persuasion. So I just can't win. Oh well. All right, as promised on several past episodes, we have many listener questions in the mailbag, so we're going to clear out as many as we can today, beginning with a phone call.
Hey Jello, it's Wyatt calling from Castle Rock, Colorado. I'm curious if you're going to do an A-37 Dragonfly episode. If you do, I would love to hear it. I think it would be a really fun episode.
All right, Wyatt, thank you for the message, and thanks to everyone else who always emails or otherwise messages, hey, cover this aircraft, cover that aircraft. And once again, my standard answer is, if it is or was an operational military aircraft we have not yet covered, it's on the list. Now, that I know is somewhat nebulous. I don't know where on the list the A-37 is there, Wyatt, but it's on the list. If we can find a compelling guest, and we have a slot in our programming, then we will certainly include it sooner than later. But yeah, it could be a little while, and I do apologize for the delay. All right, next is an email from Michael Woodruff, who, if you recall, previously asked if you could raise your tailhook once lowered. We answered that on a recent episode. I forget which one exactly, but now Michael wants to know, I noticed on the canopy of an A-10 Warthog, it looks like there are holes or dots or something above the pilot's head. I was wondering if you could tell me what those are for. Well, no, Michael, I can't, but I did put your question to John Marks, call sign Carl. For you Patreon supporters, you might remember him. He came on and did a happy hour with us because Carl Marks has 7,000 hours and counting in the A-10. So sure enough, he sends me, quote, "The small dots are stickers, each with a unique pattern on them that allows an optical tracker on the top of our helmets to determine where we are looking, which is displayed by symbology in our helmet-mounted cueing system. This allows us to slave our targeting pod quickly to anything we want to look at, as well as a host of other functions made possible by having the aircraft know precisely where we are looking." So there you go, Michael. And I'm glad to have a nice depth of folks that help out with the show to help me answer these questions. All right, next, let's take another phone call.
Hey, Jello. My name is Sam. I'm from El Paso, Texas, and I'm currently a first-year PhD student at the University of Arkansas who's just kind of looking at a U.S. Air Force through OTS scope. My question is actually about U2. So I just finished the U2 episode for the third or fourth time recently, and I have a question about the acceptance of students right out of UPT into U2. So when I look this up, I see articles about it from 2019, 2020, but I don't see anything substantial about the content. Is this every UPT class has a U2 slot? Is this one per year kind of thing? So I was just wondering about that. Appreciate the show. Appreciate everything you do. Thanks.
Thank you, Sam. Once again, I don't know the answer to this one, so I put it to my folks in the Rolodex. And from Lips, you remember him from back on our U2 episode, he wrote, quote, "Things change in life, but last I heard you needed 1,500 hours to even apply. And those might even be pilot in command hours. But heck, in COVID land, who knows anymore? If the kid wants it bad enough, like I did, he'll be a deuce driver one day guaranteed." And then, of course, Lips and I bantered back and forth a while because we hadn't chatted, and he's just a funny character. So yeah, I don't know if that's still accurate. Lips has been out of the picture a little while there, Sam. But if you are on Facebook, I recommend you join our group called The Pit. It is full of aspiring military aviators just like you. Some of them stick around even after they've made it through training and into the fleet or the CAF. And so if you ask your question there, it's likely that someone has more recent information than Lips, and Lips has better information than I do. There you go. All right, next is an email from Owen Cave from Michigan. He says, "I was recently listening to the early episode about night carrier landings, and your guest Fish Kalish told a story about a friend who had a ramp strike and had to punch out below the deck. Fish said there was an engine fire, and although he didn't really touch on the state of the aircraft afterwards, I assume it was probably very expensive to fix, if it could even be salvaged at all." Yeah, that's probably true there, Owen. I don't remember the exact situation on that aircraft, but typically they don't do too well after a ramp strike. At any rate, Owen continues, "My question is about what disciplinary actions follow events like this. Do pilots get any type of penalty when things like this happen that are indeed pilot error, or in some cases are even getting their wings taken? Or is the Navy forgiving and understanding, especially with all the money they spent training these pilots?" Fish said it was pitch black and a lot of people were struggling to trap that night. So I'm just curious what happens to that pilot after an event like this. Well, that's a good question, Owen, and there's not one answer, because what happens is, as we've talked about before, including on our other series, The Merge, there are all kinds of boards that convene when a mishap occurs, and one of them is a FNAB, Field Naval Aviation Evaluation Board, FNAEB, I think. We just call it a FNAB. And what the FNAB does is it interviews different people, even I think the pilot, him or herself. They look for clues. Is this pilot really struggling, or was just this a one-off type of mistake? If there's cues that this is someone who's maybe over their head and it's just not working out and they've been counseled and talked to before, well then yeah, they could theoretically have their wings clipped. But if it's an otherwise solid player who just had a bad night, and like you even put in your question, everybody was struggling and man, a mistake was made, but he'll never do it again, right? Because of that traumatic event, well then generally they'll get a second chance. It just depends on who it is and what the extenuating circumstances are. All right, next is a phone call, and we'll finish with this one. Here we go.
Hi, Vincent. My name's William Vorvart. I'm not in the military, but I used to work at Hamilton Standard in the 80s. We worked on Hamilton Standard 54H60 propellers for the P3 Orion and the C-130. They're two quite different, not really different designs, but there's uniqueness about each one, yet they're still called the 54H60. Just wondered if you can maybe help me shed a little light on that. Actually got the fly behind a P3 Orion setup on a Convair 580 converted to a turboprop. What an experience. And ironically, Vincent, my foreman, my job a couple of years ago was named Vincent Aiello. All right, look forward to hearing from you.
All right, William, thanks for that phone call. And yeah, that's really cool about your foreman. I guess Vincent Aiello is a fairly common Italian name, I'm told. And regarding the propeller nomenclature, I know you've been waiting a long time for me to answer this, William. I put it to one source, didn't get an answer, really didn't have another way to answer it, and finally put it by my occasional co-host, Ken, who seemed to know. And since he's joining us for today's interview anyway, let's bring him on now. Ken, welcome back to the show, sir.
Hi, Jello. How you doing?
I'm great. It's good to have you back. And what can you tell us about this nomenclature on this propeller? I flew one airplane with a propeller, but mostly jets.
Well, the 54H60 is actually a company designation. It's the Hamilton Standard Turboprop Propeller.
Okay.
And they designed it about 65 years ago for turboprop engines. So it's used on the P3, the C-130, the E-2 Hawkeye. It's a common and very important propeller. It's what's called a constant speed prop. The blade pitch changes, and you have a governor to keep the prop speed constant. It's worth mentioning that when we say 54H60, that actually isn't the designation for the propeller. To be technical, it's the designation for the hub, because the different blades have their own designations. It's still in widespread use, but the company, which is now called Collins Aerospace, has a new propeller called the NP2000. It's 8 blades, and it's electronically controlled rather than hydraulically controlled like the older propeller. And if you look at the newer Hawkeyes or some C-130s that have been retrofitted, you can see if they have this 8-bladed NP2000 prop on them.
I think that's what the E-2 Hawkeye has these days. And I'm close enough to Naval Air Station North Island that I hear them buzzing out there all the time like angry beehives. So yeah, apparently it's a pretty effective propeller. So
yeah.
Well, I appreciate you helping us clear that up, Ken, because as I said earlier, I've been sitting on that one a while. It's good to have you back on the show. That's going to do it for listener questions. And this week you were the host. And let's just get right into it. I mean, first off, what inspired you to pursue an interview about flight controls?
Well, Jello, I got to call you on the intro when you said that this technology isn't sexy. This is the coolest stuff. There is no technology that's more important to modern military aircraft and civilian aircraft. When you talk about things like 5th generation fighters, what you're talking about is digital fly-by-wire aircraft. And digital fly-by-wire lets us have amazing things. For example, some of these stealth shapes just wouldn't fly straight without a digital fly-by-wire system. It gives you better performance. It gives you better handling. That's why an F-18 has a much better boarding rate and a much lower mishap rate than the fighters that preceded it because of its digital flight controls. Outside of that, I mean, even in civilian aviation, it's very important. It allows modern airliners to be more efficient. My tiny little mighty Piper Archer has a digital autopilot, and when you're flying single pilot IFR, that's a big help. So flight controls are very cool. It also happens to be the subject of my graduate degree and what I do for a full-time job. So it's a subject that's near and dear to my heart.
All right. Well, importance and sexiness are, I don't know if they're correlated or not, Ken, but clearly you are the right person to have this conversation with the right guy who literally wrote the book on fly-by-wire flight controls. So without further ado, let's get to your interview.
Modern aircraft like the FA-18 Hornet and the V-22 Osprey have digital flight control systems, sometimes called fly-by-wire. What is a flight control system and how does it work? That will be the topic of today's episode with our guest, retired U.S. Air Force Lieutenant Colonel David Divot Kern, an experimental test pilot. Welcome, Divot.
Hey, thanks. I'm glad to be here.
So we like to start off these podcasts by having you tell us a little bit about yourself, your education, how'd you get in the military, what'd you do there, what are you doing now?
Well, that's always the fighter pilot classic, isn't it? Stand up and tell us about yourself, right?
Sure.
I've heard that joke before. I know how that one goes. I grew up around airplanes. I grew up knowing I wanted to fly fighters. That was always my dream from when I was pretty short till all the way through high school. And I was been very fortunate to live that dream out. I'm 3rd generation Air Force aviator and grown up around Air Force bases and air shows. That's kind of the path that I struck out on. So I applied to and I was accepted to the Air Force Academy. I was class of 99, majored in electrical engineering just because I've always been a little bit of a nerd and wasn't really sure what I wanted to do with my life once I got there. But I was able to go to pilot training. I was able to fly F-16s operationally. I had one operational assignment at Shaw Air Force Base, and I went back to the schoolhouse to teach at Luke Air Force Base. And I found my way into flight test from Luke Air Force Base, applied to the Air Force Test Pilot School, and been doing flight test ever since.
You're retired now, right?
I am retired. Yeah, so I retired 2019. I had the opportunity to test some pretty amazing things with the Air Force, 2 assignments to Edwards, an assignment to Eglin Air Force Base in between. And now I'm a test pilot with the FAA. I do aircraft certification for prototype aircraft. So I like to remind people I'm not an inspector. I don't watch other people fly. I just test the prototype aircraft.
That's a pretty impressive background. Let's talk about flight control system. I mean, starting off with a definition, what is a flight control system? What does it do?
Fundamentally, as a pilot, when I pull back on the controls, I want the houses to get smaller. And when I push forward, I want them to get bigger. And so what I just need is some connection between my hand and the airplane that makes that happen, fundamentally. So we all grew up, most of us, who learned to fly in something simple like a Cessna 172 or a Piper Archer. And there were pulleys and cables, push rods that connected the yoke, or in the case of if you flew a Cirrus, you got the side stick yoke combo, whatever it is. And that's how it moved the flight controls. So bigger, more complicated aircraft, more powerful aircraft, like the fighters that I got to fly, have more complicated systems in between your hand and the aircraft. But fundamentally, they're trying to do the same thing.
Okay, you pointed out, let's take a simple aircraft like a Piper Archer that I fly. You have a inceptor, as we call it, a control yoke and rudder pedals. The actuation is my arm muscles or my feet muscles pushing against there, and the computation's in my head. And there are cables that go out to the control surfaces, and that's it. Why couldn't an F-16 fly with essentially that same system? Why did we have to get bigger and better and more sophisticated?
I think that we've arrived at the solutions we've got today for the sophisticated fly-by-wire systems we've got in modern fighters and even in a lot of the airliners that we get carried around on today, because we tried it the other way first and it didn't quite work out for us. So if you take a traditional flight control system like the Piper Archer you're talking about with the pulleys, cables, push rods, and so on, and you start building a bigger, more capable, more powerful aircraft, you're going to start to run into some problems. Let's just talk about size for starters. You build a bigger airplane, now I got to have longer cables, I got to have longer push rods. Well, there's some weight involved with that, but I also need to route those cables and push rods through the aircraft structure all the way back to the tail. And every time that they touch something else, whether it's a pulley or it's some sort of guide for the push rod, well, there's going to be friction involved. Friction's not good in flight controls. Nobody wants to have that sort of resistance as they're trying to control the aircraft, because it makes it harder to be more precise and harder to be smooth. So with larger aircraft, you just run into this friction, but also every time you've got the connections from one part of the flight control system to the other, any mechanical connection is going to have a little wiggle in it. And that little wiggle is going to add up through the whole length of the flight control system. So now I've got something where I'm moving the yoke or the stick, or we call it the inceptor. I just like to call it the stick. Grew up as an F-16 driver. And every time I move the stick, now I've got some sort of distance. I have to move the controls before the aircraft starts to respond. We call that deadband in flight control engineering. And that's not a good thing either, because now the pilot's losing the precision of controlling the aircraft. But then on top of that, with that larger aircraft, well, now it's going to weigh more too. So whether you're talking about even something that's marginally bigger than that Piper Archer, an F-16 is kind of a 25, 30,000 pound airplane, loaded up, moderately loaded, not even heavy. Well, now you got a lot more mass that I'm trying to move with air pressure going across those flight controls. Well, that's going to push back on my hand. And so essentially we arrived at the systems we've got today because we tried it the other way first, and you start running into these fairly large problems. I love old war movies, and if you watch some of those old, John Wayne war movies and so on, where he's at the controls of that aircraft and he's fighting with it, he's making huge control movements just to stay on course. And he's obviously having to work hard on the controls. Well, that's just a movie, but people knew that's how airplanes used to fly. Well, none of those are really good things for having a high performance fighter or being able to operate a very large aircraft, maybe a bomber or a transport aircraft that needs to carry a lot of mass and be able to land maybe in high crosswinds, that kind of thing. So to have that greater precision and control, we started experimenting with some other ways to build the flight controls. I don't want to go into a whole history of flight control systems because that's not really what we're here to talk about. It's the Fighter Pilot podcast, right? But we started to see hydraulic flight controls. So the Korean War, Vietnam War era fighters all had hydraulic flight controls. So that lets you push back against all the air loads on the control surfaces real well. I can pull back on the stick, and it doesn't matter that there's tons of force trying to fight me. I've got a hydraulic system that's moving that tail right where I want it. So that's a good thing, and that lets you fly aircraft that have much higher performance, maybe higher mass, and it solves some of the problems of the deadband, the wiggle, the resistance in the flight controls going back to the tail. But there's also some other problems it doesn't quite solve. That's where we start getting into topics like having a neutrally or even unstable aircraft like the F-16. Great for maneuverability, but you just can't stay ahead of that airplane, and you're not going to be able to precisely employ it as a weapon system because you're constantly just trying to keep the pointy end going forward. So that's where the computers come in. That's where fly-by-wire starts to help, where it interprets the pilot's commands, makes the jet do what the pilot meant for the aircraft to do by applying a bunch of math, basically, to what pilot's hand is commanding on the controls.
So let's talk a little bit about that instability that you were talking about. If I'm flying my Piper Archer and I'm trimmed out straight and level, and I pull back on the yoke and my nose pitches up, there's going to be a nose down pitching moment that wants to return me to my trimmed condition. If I'm flying a B-1B, which happens to be slightly unstable in pitch, and I don't have all the electronic augmentation turned on, I pull back to a high angle of attack, there's not going to be a restoring moment that wants to push my nose back down. In fact, it's going to want to just continue to increase. And I assume that it's the same basic principle in an F-16.
Well, I think the way that I like to try to explain this, just as one pilot to another, is airplanes are controllable when they're in trim. Trim and stability is what lets us control airplanes. And it's whatever you're trying to do with that airplane, whether it's just to take off or land, or you're trying to do something that's a little bit more challenging, like you're trying to employ it as a weapon system or you're trying to land it on an aircraft carrier. I want to just say, by the way, I got a chance to fly the Hornet twice, and I never got to go to the boat, but I did get to do carrier landings, carrier-style landings at Pax River. That's pretty fun. Anyways, the point is, you're trying to do something a little bit more precise. You're trying to strafe with an A-10. You're trying to dogfight with an F-15 or an F-22. The aircraft's controllable because of something called trim and stability. So stability is just like the marble in the bowl. If you've got positive stability, the marble's going to roll back to the middle of the bowl. That's awesome. You turn the bowl upside down, you put the marble on the back of the bowl. Now you get the marble a little bit off to one side or the other. It's off to the races. It's not coming back. That's unstable. And neutral is kind of like the marble on a table. So if I want to have an aircraft that's agile, it's maneuverable, well, a little bit of instability really helps with that mission element. Unfortunately, though, you get an unstable aircraft, even one that's slightly unstable, like you were describing the B-1, that neutral stability. Now just flying that airplane is like walking around trying to balance a yardstick on your finger. And depending on what else you're trying to do, that could get pretty challenging. All maybe you can think about is just that one task of trying to balance that yardstick on your finger as you're walking around. So in the case of, now we're talking about an airplane here, with that Piper Archer, you've got positive stability all the way around with that airplane. If the nose gets pointed away from wherever it was, it's going to naturally come back to that. And when you apply some sort of control to that aircraft, and you're talking about moments, which is just a twisting force on the aircraft, whether you're trying to twist the nose to go up a little higher or a little bit lower, it's going to keep moving until it finds that new stable point, the new balance point for the aircraft. So as far as how we relate this back to fly-by-wire and flight control systems, you can have with fly-by-wire sort of a artificial or a synthetic balance point that to the pilot, it can seem like it's stable under certain conditions, while the aircraft flight control computers are doing all the hard work to keep things balanced about that point. And so what that lets the pilot do is focus on the mission task, whether it's flying the airplane or trying to employ it as a weapon, and not have to think about how do I keep this airplane just going in the right direction. And so there's certain kinds of programs that the flight control computers will run. We call those control laws. Those will give the pilot an artificial feel for how the airplane should fly, and they apply certain mathematical concepts to make the airplane fly in a predictable and desirable way. And those change depending on what you're trying to do with the airplane, whether it's just to be stable at cruise, or it's to be agile in a dogfight, or precise for a landing.
I own an unstable vehicle. It's called a bicycle. And I stabilize my bicycle, and I stabilize that by using sensors like my eyes and the motion sensors in my inner ears. And then I make a computation, if you will, in my brain, and I then adjust how I hold my body and how I move the handlebars. And so I keep this unstable vehicle fully under control. Is that somewhat analogous to how say an F-16 would work? And in an F-16, how would that be mechanized?
The way I like to try to explain this process is that the flight control computers are trying to accomplish a certain goal. And it could just be keeping the pointy end forward. And then the pilot is applying a certain command, a difference to that system. So for your bicycle analogy, I guess, the rotating wheels, gyroscopic force, whatever, the bicycle is basically going to be stable. And then you lean one way or you lean the other, and then the system's going to respond. So in terms of like fly-by-wire systems, what we're talking about here is the flight control computer may be using a control law called G command. That's basically the up and away control law for an F-16 and for a lot of other fly-by-wire aircraft. So if I don't touch the controls and it's trimmed up, it's just going to hold 1G, which is a pretty cool concept because now I can accelerate, I can decelerate, and the airplane doesn't go out of trim. Now, going back to that Piper Archer you're talking about, you accelerate or you decelerate, what happens to that nose, right? The controls are going to get heavy or you're going to be pushing forward. You're sensing those airspeed changes because that's causing a trim change. But in this case, with the fly-by-wire system, using G command, now the aircraft just keeps doing what it was doing, which is 1G, as long as I don't touch the controls. And then when I start adding in backstick pressure, commanding G, I can apply the same force and get the same G regardless of whether I'm going really slow or really fast. Whereas with that Piper Archer, or to use maybe a more broader envelope aircraft that doesn't have a fly-by-wire system, a lot of military aviators have flown the T-38, and they know it's mushy when you're slow around the traffic pattern. You're having to really stir the pot with the flight controls. But then you get up and away, you get going fast with that T-38, 450, 500 knots. Now it's going to be fingertip touch to control the aircraft, and you don't want to honk back on the controls or you're going to over-G the jet. Well, fly-by-wire helps you fix that, helps you protect yourself in a way, because now that same backstick pressure can give me 2Gs or 5Gs or 9Gs, whatever it is, regardless of how fast I'm going, as long as the aircraft is capable of actually doing that. So, I can't be 100 knots and get 9Gs, but you get the idea.
Right. With some fly-by-wire aircraft, like an early model F-16, an A model, or a B-1B, we say that it has an analog fly-by-wire system. And with more recent aircraft, like, let's say, an F-16C or an F-18 or an MV-22, we say we have a digital flight control system. What's the difference between those?
Yeah, I always thought it was fascinating with the old analog fly-by-wire computers in the F-16. That was just such a interesting thing for me to look at because, to call it a computer is really a little bit of a stretch. It's some circuits and they're just combining signals and causing an output. There's definitely engineering and math that goes into that, but it's not a coded, software type of application like we think of on your cell phone or whatever. So those are pretty interesting systems. They're definitely out of date now, but they're pretty interesting because they can be pretty darn reliable. It's just circuits and components. The problem is tuning it to get it to do what you want it to do. And then you don't have a whole lot of flexibility once it's tuned that way. Now, that's a big difference from a digital fly-by-wire system where, man, I can just crack open the code. I can change something. I got a whole different ballgame now. I've got a different aircraft that I'm flying. And that's what we see today, which has a ton of advantages because you can put a lot of these little if-then types of statements in there, and you can account for a lot of things, but you can also create some unexpected or undesirable results sometimes, which means they need a lot of testing to make sure that you've not left unaccounted for bugs in the code. But that's the difference there between analog versus digital. In both cases, you don't want to have just one computer that's running your fly-by-wire system. The real key here is you want to have 4 computers is pretty much the state of the art. This way they can do some error checking between them, and if there's any kind of problem with one, the other 3 can vote them off the island and keep the show running, and the pilot may not even know that that's happened. That's kind of the state of the art, both for military and for civil applications now. There's always another computer that's monitoring the fly-by-wire control system and making sure that the right answer is happening.
The computers that we use in our daily lives sometimes hang up. You get the spinning beach ball. That would obviously be a very bad thing in an aircraft flight control system. What are the sorts of measures that we take so that that doesn't happen in a digital flight control system?
I got annoyed with that just today. And it's amazing how it's just kind of part of modern life. Well, you just turn it off, turn it back on, just reboot it, right? And that's not going to be acceptable for any kind of fly-by-wire flight control system. You just can't allow for that. And so, like I was saying, the redundancy is the key, but there's all kinds of problems that you can run into as you're looking at how these control systems are functioning. You could have garbage in, garbage out, where one of the flight control computers has become disconnected from a sensor, or typically you've got multiple sensors that are all feeding in redundant data. So I've got more than one angle of attack sensor. I've got more than one airspeed sensor and so on, because you need all that to calculate how the aircraft should be flying. So if a sensor goes bad, well, the computer it's feeding is going to start coming up with a weird or wrong answer. Now, it doesn't mean the computer's malfunctions. It's just garbage in, garbage out. And so that's why you want to have that redundancy throughout the system to guard against that. But you could also have something where the sensor's working fine. It's providing the data to that computer, but maybe that computer goes offline. Just who knows why? Maybe that computer lost power. All kinds of things can happen with electronics, as we know. So you could have valid inputs and then no output, or you could have a completely bizarro output from one of the computers. And so what they'll do there is they'll check to see if they're sort of in line with each other. A lot of times they'll throw out the low and the high answer and then average the 2 in between. That's a common solution that I've seen. Or there's some sort of tolerance for, hey, this is kind of normal and we'll average all of them. But if it's way outside of tolerance, we'll throw that one away too. That's kind of how this works. And usually you want to have 4 computers because if you've only got 3, you could have 2 bad answers and kick the good answer off the island. That's something to watch out for. But typically that's why you get 4 computers. And I'll tell you, the more modern solutions actually will use different hardware and different software doing the same thing. It's just coded in different languages across the 4 computers. So you can avoid those kinds of problems.
In 1991, when I was flight testing the V-22 Osprey, which has a triplex flight control architecture, because of a paperwork screw-up, gyroscope wiring to 2 of the 3 flight control computers got reversed. And on its first flight, it took off, and then the gyroscopes that should have been providing stabilizing sensor inputs ended up, because the wiring was reversed, were providing destabilizing, and the 2 that were wired incorrectly voted the one that was working properly off the island. And that airplane crashed several seconds after it took off because of that.
Yeah, I remember that happening, and there's definitely a risk. a lot of times it comes down to cost, weight, complexity, kinds of savings. And there's always a risk when you make those kinds of decisions. I think, honestly, though, the biggest lesson learned out of that is you can think that you've got the right answer, and the engineers can tell you, hey, it's great. This one's wired up. It's good to go. But you got to trust but verify. And it's so important that we take these aircraft and the systems out to the limits and a little bit beyond them just to make sure that the math lines up, because we've gotten way more sophisticated with the computer simulation and modeling, and you can get some really compelling answers, really colorful charts and these high resolution graphics that come out of the simulation. You go, wow, that's great. So that's how it's going to work, right? And then you find out that, hey, that one should have been a 0 and the negative sign was in the wrong place. And yeah, those things can happen. So we got to trust but verify. Big fan of flight test.
I've got a couple questions from Fighter Pilot Podcast listener Scott Morris. The first one is, are we getting to the point that because of digital flight control systems, we don't have to worry about the flying characteristics of a shape? For example, can we use canards or some other physical features, or will the digital flight control system compensate for whatever is the shape of the vehicle?
Well, I think the answer is probably yes to Scott's question in a lot of cases, but there's no such thing as a free lunch. You end up with sometimes some unintended consequences. The thing I've learned from being around flight tests and flying a lot of different airplanes, I've got over 80 different types of airplanes in my logbook. I've had a chance to fly every fourth gen fighter we've got in the military. Good looking airplanes fly well. Airplanes that look a little weird also tend to fly a little weird. So I guess the answer to Scott's question is yes. If you put enough thrust on a brick, you can fly it. The F4 did that. And if you have a really weird shaped airplane, F-117, man, that's fly-by-wire, and people were able to employ that successfully in combat for a long time. Doesn't mean that it's not without cost, and there's going to be some consequences to unusual design choices, sometimes at the margins of the envelope. So let me give you an example here. So I'm going to do a little bit of a comparison, Hornet versus Viper, because I've had a chance to fly both of them. I admire both of those airplanes. They're both really great airplanes. Now, the Hornet has leading edge flaps, really big leading edge flaps. So does the F-16. Both of them have leading edge flaps on the front of the wing at the leading edge extension. Now, there's a difference, though, between those two systems. One is that the Hornet has larger leading edge flaps than the F-16, but the other is that the Hornet leading edge flaps move independently, whereas the F-16 leading edge flaps are connected. It's a single drive, and if they start to get asymmetric, it locks down and it gives you warnings as a pilot, and it's kind of not a good thing. It's time to go home. So the outcome of that is you've got a little bit more sophisticated system on the Hornet, and you get really great high angle of attack maneuvering for that Hornet as a result. I mean, you can do just about anything you want to do with a Hornet, and it's going to go back to pointy end forward. Whereas with the F-16, where we've got a symmetric leading edge flap system, if you start to get a little bit of a side slip on the aircraft at high angles of attack, well, you could end up in a deep stall with that F-16, and you're going to have to apply some corrective actions to get back to being pointy end forward. So that's something I think anybody who's flown the F-16 is familiar with. They understand that concept, and everybody knows that the Hornet's got great high alpha maneuvering characteristics, but it's also an example of how you can apply digital fly-by-wire to solve some problems or to create some workarounds and create some capability where you otherwise might not have had it. So there can be some problems at the fringe of the envelope, and I'll cite kind of the F-16 departure characteristics. Get past 26 degrees angle of attack, or you get some good side slip on it with not even close to that, and you're going to depart. And it's because there's a fringe on that fly-by-wire system where it can't maintain the control anymore. You saturated the flight controls. Basically, if you happen to be departing an F-16, you look over your shoulder, you'll see those tails, those horizontal tails go all the way to the stops, and they'll just kind of stay there because they're trying to stop the nose rate from going sideways or up or whatever. I've done a lot of that, intentional departures with F-16, so I can tell you it does that. With Scott's question, can we do unusual shapes? Yes, and you can have the fly-by-wire system accommodate that. but there could be some other unintended consequences where you could perhaps lose some performance, you could lose some efficiency, you might gain in maneuverability, but there's always a trade-off with airplanes.
I would answer Scott, not at all disputing anything that you said, but in a somewhat different way, which is how I would respond to Scott is that you could put a full authority digital flight control system in my Piper Archer, and there'd be a lot of advantages to doing that. It would be an easier airplane to fly with some of the modes. But just because it had this full authority system, you still couldn't fly it like an F-16 because you're fundamentally limited by aerodynamics and propulsion. And so digital flight control systems aren't, what I would say to Scott is that they're not magic. They can provide an awful lot of advantages, but ultimately you have to have the aerodynamics and propulsion or you can't do what you want to do.
No, I think that's absolutely true. And we're talking about two sides of the same coin there.
Yes, I agree.
You bring up a great point. I think it's only a matter of time before light aircraft start seeing fly-by-wire systems. And we kind of see some of that already with some of the light aircraft. I mean, just as something as simple as a yaw damper, well, that's actually kind of fly-by-wire, although it's very limited, one axis. But, some of the light aircraft now, they've got stuff like emergency auto land. Pilot passes out, passenger pushes a button, and now the aircraft's going to find the nearest suitable airfield and squawk emergency and talk to air traffic control and go land. I mean, that's a real thing that's already out there in the wild. So that's a small single engine airplane. It's fly-by-wire. So yeah, a lot of capability can make a mediocre airplane better, and it can make an average pilot look like they're King Kong. But you're still limited by the propulsion and the shape of the airframe.
The Piper Archer that I fly has a digital autopilot.
Oh.
It's a low authority system, but it works great. And it really illustrates the advantages of having digital flight controls, even in this little Piper Archer. The next question from Scott is, are digital flight control systems normally hardened to protect against electromagnetic pulse?
I don't really want to get into that too much, but I will say that it's something that you think about in terms of the redundancy and reliability of the system. You can have a bit flip inside of a computer for a lot of reasons, and you don't want that to cause the computer to completely go offline or to fight with the other fly-by-wire control computers. So it is something that you think about, but I don't really want to dig too deep on that one.
No, I agree. What I would also say to Scott, though, is that aside from electromagnetic pulse, any aircraft has to be hardened against lightning, and it needs to be hardened against interference from other aircraft systems or, say, from ground-based radars. So those electromagnetic threats, even if they're not as dramatic as an electromagnetic pulse, are there, and the systems do need to be hardened against them, even in a civil system.
Well, let me just say, I'm going to go kind of a different direction, but similar concept there. I think more and more, a lot of the issues that are worth talking about in terms of aircraft, aerospace advancement is the concepts of cybersecurity. We're talking about digital fly-by-wire systems. Well, it's digital. There's software in there. Well, there's software in a lot of parts of your aircraft. And I really need the flight controls to work right all the time. That's kind of important. And so I think that that's one of the issues that is more of a area of interest is how do I know I've got the right software that's running in my fly-by-wire system and it's not affected by anything else on the airplane, even as I need the flight control computers to take into account a lot of other stuff that's going on with my airplane and where I am and where I want to go and how I'm getting there and so on. I think cybersecurity is probably a very interesting concept as we see how these advance, and particularly as we start talking about, this is in both military and civil, concepts of optionally piloted or loyal wingman kinds of things, or this urban air mobility where maybe it's like Johnny Cab, but it's got rotors and you hop in and say, take me to lunch, and this thing's flying itself. Well, how many other pathways are there into that flight control computer? Or if I've got a loyal wingman drone off the 2 miles off the left side of my F-16 that could be armed, what other inputs are there into those flight control computers?
I work in flight controls professionally. My thoughts on cybersecurity is it keeps me busy during the day. It keeps me up at night, and that's all I'll talk about it because it's a vulnerability, and we just don't want to talk about that in an open forum.
That's a big deal.
I also have a question from Fighter Pilot podcast supporter Jeevan Deva. He says, do you think that we will see thrust vectoring in increasing types of new aircraft in the future, or is it something that's gone out of favor because of its cost or complexity?
Well, I think that's a two-part question for military and for civil aircraft, because I think in military aircraft, it's not going to go away. I mean, is it kind of a circus trick? A little bit, but it's got some definite applications. It's definitely got some applications for tactical military aviation, and I don't even want to go into any more detail than that. Those that know why it's useful, and it's good to have. So I don't think it's going to completely disappear from the scene as far as tactical military aviation goes. I do think we're going to see a little bit more of it as we're looking at some of those weird advancements I was just talking about with civil aviation. You know, we're going to start to see a few more propellers showing up in new designs, fewer jets. I think with this electric aviation and some of the urban air mobility and some of those things, like that Osprey that you were talking about earlier, where that is kind of thrust vectoring, but of a different kind. Now I've got this whole rotor that's twisting or shifting or what have you. So I don't think it's going away, but the way I think of this from a digital fly-by-wire flight control perspective is that this is just a different kind of flight control surface, right? Instead of just having, I've got elevator, rudder, ailerons, maybe I got some spoilers of various kinds and so on. Well, this is just one other flight control input that can create those moments, those twisting forces on the aircraft. So it's just math. It's just software. I say that a little bit tongue in cheek because software's harder than it looks, but it's just another way to point the aircraft where I want it to go. And so it's going to create, like the first question we got, can you do weird aircraft shapes? Absolutely. And with thrust vectors or some other distributed lift type of things, you can have some pretty ungainly aircraft shapes that now they're maneuverable. But when you run out of control power, and I was talking about like F-16 tails being all the way against the stops, just trying to hold the nose from sliding off into a deep stall, well, you can run into those ends of your control authority when you're talking about thrust vectoring, and you think you've got carefree maneuvering, or up to the point that you got no more rope left to hang yourself. So, yeah, I don't think it's going away. I think we'll see more of it.
In your book, Introduction to Fly-by-Wire Flight Control Systems, and we'll talk about that book a little bit more later, you talk about different fly-by-wire risks and their mitigations. What I'd like to do is read off some of those risks to you and have you talk about what are the problems and then how do we deal with those problems. So the first one that you bring up is loss of electrical power to flight control systems. Obviously, if you have an electrical system and you don't get electrical power to it, that's a big problem. So how do aircraft designs mitigate that risk?
Well, it's a digital system. It's got computers. It's got software. You've got to feed the machine. Just like when your cell phone runs out of batteries, it's no more fun, right? So you got to have power going to your fly-by-wire flight control computers. And typically the way that that's happening is just off your main aircraft bus, but not directly. Anybody who's been a professional aviator for a long time knows those charts in the flight manual we don't really like to look at, but it's all the wiring diagrams of you got this electrical bus and you got that electrical bus and I got the hot battery bus or whatever it is. And so for flight control computers, they're going to live all the way at the bottom of that tree. Bottom being where it's got that direct connection and the most reliable, the last ditch power source. And everything else trickles down into that and should feed it. But typically, the juice is coming off the main aircraft bus, whatever the generators are producing or alternator, whatever it is. Typically, what you'll see there is you're going to have some sort of backup battery, some sort of uninterruptible power supply, if you want to think of it that way. And honestly, that's what it is. It's a UPS that's connected onto those flight control computers. And then it's getting recharged by any other power source available. Typically, there's a hierarchy, if you will. So for the F-16, flying that, you got a main aircraft kind of power that's feeding in there. But the flight control computers, the old ones, I'm digging back in my memory here because that was a while ago. with the analog computers, but they had individual batteries for the flight control computers. There was 4 flight control computers and there was 4 batteries. So then with the digital, that kind of went away, if I remember right. But then ultimately, if you lost your electrical system, your electrical generation capability off the engine in F-16, that's where your emergency power unit comes in, your EPU for an F-16, which is run by hydrazine, kind of nasty stuff, but it works. And that spins up a little turbine, and then you've got electrical power going to your flight control computers again, and some other capabilities too. That's one solution. The F-35 is a little bit different in how they've implemented that. Still a single engine fighter, but they've got backup power that can be generated if they lost the engine. And then I'll say for some other fly-by-wire aircraft, more on the civil side that you see this, they'll have something called a ram air turbine that they can drop out of a door. Normally it lives up inside usually the belly of the airplane. And if they have lost all electrical power, then they can pull a handle and this little trapeze swings out of the door. And it's basically like this pinwheel. It's this 2-bladed pinwheel that sticks out there in the breeze. And that'll run a generator. And that's kind of your last ditch power back to your flight control computers. But that's more of on the civil side of aviation that you'll see that.
Another risk that you talk about in the book is software or hardware failure. And I think we somewhat addressed this when we were talking about redundancy, but do you have any other thoughts?
There's a lot that goes into proving software, and I don't want to get into that because honestly, it's kind of boring, but it's totally necessary. I do think that it is pretty interesting to see some of the best practices I've seen now with some of the newer designs where you'll have the same code, essentially the same logic, but it's coded up in 2 different languages. So you got language A and I got language B, and then I got 4 flight control computers, and those are made by 2 different manufacturers. It's different hardware and it's different software compilations. So basically I've got, these 4 different combinations, and it's never the same piece of software code source running on the same kind of hardware, and they're all checking each other. And I think that that's kind of like, it's engineering, but it's kind of art. It's pretty neat to see how that's been thought through. And I think that that's one of the best ways, I think, of protecting against these software and hardware failures. They're going to happen. It's more human error than failure most of the time, but having those layers of redundancy helps protect us.
I'll mention on the software side, we're used to on our phones, there's a new version of the app that comes out every 2 weeks that we download. And the reason is that kind of methodology is optimized for rapid innovation. And if there's a bug in it, there's a bug in it. It's not going to kill you. But of course, a bug in flight control, critical stuff can kill you. So we have very, very rigorous protocols to test out. And even a small software change can be many, many months in the making. There's a set of guidelines, and we'll take a deep dive into Nerdville for 15 seconds, called DO178-C. And that's the protocol so that we have software that will never hang up.
No, you're absolutely right. And that's the standard. That's how it works. I think maybe the one thing that might be of interest here to the audience is that there's a little bit of a balancing act between capability, and sophistication, and then the ability to prove that it's always going to do what you think it's going to do, and there's no exceptions or square corners that you can find yourself in. It's that old keep it simple, stupid principle. But performance is what drives us. Performance is what sells airplanes. Performance is what gives you that tactical capability, that edge when we're talking about fighter aviation. And so to get that, you got to squeeze every ounce of possibility out of the shape of that airframe and the performance possibilities of the engine. So that's going to lead to those design trade-offs. So, I don't want to dig too deep into this. You said DO-178, so I'm going to say Boeing 737 MAX. And I'm not going to dig really far into that because there's a lot that could be dissected there that's beyond the scope of what we're talking about, just in terms of flight controls. But the MCAS system ultimately was a Band-Aid when we look back on it. It was a fix for one problem with how the airplane flew. It was intended to just fix one small problem Then there was a need to fix one more problem, maybe, and we're just going to change it a little bit. There were a lot of other things with that system, and I don't want to dig deep into that, and it's not meant as a finger-pointing blame game, but just to say that that's kind of an example where you're trying to squeeze all the performance out of that system. And, Boeing 737 MAX is a great evolution of a proven airframe with some awesome engines on it. It just tended to kind of have a little bit of a pitch sensitivity, or the flying qualities weren't exactly what they were supposed to be. So that's why MCAS got added, and we all know the rest of the story.
Well, I think that actually feeds into your next failure mode you talked about, which is sensors reporting incorrectly or not at all.
Yeah, and as we know, so that was a problem when they had only the single AOA sensor. And really, I'm a big advocate for having quad redundancy, because you fix a lot of problems there and you create that reliability. I was just going to say, though, something that I think we're going to see more and more with fly-by-wire systems that are trying to squeeze all the performance possibility out of an airframe is that you're going to start to see some of those hiccups in terms of unintended consequences at the fringes of the envelope. And this is why flight test is so important, but it's impossible to fly under every conceivable set of circumstances. You can't test every possibility, but you try to validate the models. So yeah, there are some examples of fly-by-wire aircraft where they have switched modes unintentionally. You end up with the airplane thinks it's flying in a regime that it's not supposed to be in, and then the pilot starts to wonder, what is the robot doing and what's it about to do next? We could talk more about redundancy, but I just wanted to bring that kind of full circle. And so then, yeah, sensor reliability is the other big piece of it there. And quad redundancy, I think, solves a lot of that. But smart sensors keep getting smarter and more sophisticated. And if you think back to like early days of airspeed indicators, it used to be just a flap out there on the strut of the wing that got blown to a certain angle. And that's how I know how fast I'm going, right?
I've seen those on World War I kind of airplanes.
Yeah, I know. And then, you think back to like the stall horn on that Cessna 172 I learned to fly with. It's like a tin whistle, you just get to a certain angle of attack and it starts making that noise. And that's so much less sophisticated than what we're dealing with today. Honestly, the state of the art now is to laser map the nose around the sensors, around the probes, just to balance out the probes from one side of the nose to the other. And it's phenomenal, the precision that's involved with manufacturing an aircraft. And I'm talking about the civil side. I'm talking about laser mapping the nose of an aircraft just to balance out sensor readings from one side of the nose to the other. Now, when you're starting talking about low observables, talk about sensors that are having to be mounted more flush or internal, just for radar cross section and a lot of other things, that gets a lot harder to ensure reliability for those sensors and not lose the capability of your fly-by-wire flight control system.
Another risk that you talked about in the book was that the mechanical servo actuators would lose hydraulic power, or they would jam or have uncommanded movement. What's at stake here, and how do we mitigate that?
I think that this is one of those areas that we're going to need to be more sensitive to as aircraft development becomes more sophisticated. And it's those kind of internal health monitoring loops. And I'm not preaching this, because I'll tell you, all of the aircraft manufacturers are very aware of this. They don't need to be reminded, and they're doing this already. But essentially, if I've got a generally hydraulically powered servo that's moving an aileron, for instance, out there on a wing, or moving an elevator or a whole stabilizer on a larger aircraft, and it's doing something I didn't tell it to do, that's kind of a problem. So with fly-by-wire flight controls, you're, as the pilot, telling the airplane what you intend to do. Flight control computers are translating that into surface movements, but the flight control computers need to hear back from those flight control surfaces that they've done what they were asked to do. Now, in some more sophisticated cases, like the F-35, for instance, if it's not getting back what it expected from a flight control surface, it may be able to account for that in other ways. And it may be able to dynamically change its strategy for controlling the airplane based on how it's feeling itself move. That's some pretty complicated math. So going back to your question of how do we look at servos and reliability out at control surfaces, the fundamental thing is making sure that the flight control computers have awareness that the servo's done what you told it to do. You probably want to have more than one servo on any given flight control surface, and you probably want to have them powered in different ways, just like the flight control computers need to have backup power sources and probably be using power out of different taps off that source just in case there's a problem. You want to have different power sources to the servos that are moving the flight control surfaces in your aircraft. And so that could be, I've got hydraulic system A, I got hydraulic system B. The Airbus guys like to apply colors to their hydraulic systems. I don't know why. Maybe that's a French thing. And then in more modern systems, they've just got electrical power distribution to these integrated servo actuators that trap their own fluid. And so there's a electric pump, there's fluid, and there's the actuator all out at the surface that it's moving. And there is no hydraulic fluid circulating, or there could be. And if it leaks out, it's already trapped some and it can continue to work. So you see some examples of that. The F-35 does that. Some of the more modern airliners and business jets also use these electric backup hydraulic actuators. But fundamentally, though, they got to talk back to the flight control computer, report back on their health, and let the computer know that they have done what they were supposed to do and they're continuing to be reliable. Otherwise, you can have some problems where you get hydraulic motors going stupid and putting surfaces out in the breeze. And there have been some examples of that recently as well with some safety incidents that fortunately got trapped, but it's definitely something that needs to be looked at with the design of the system.
Several times in our interview, you've talked about the importance of flight testing these advanced flight control systems. What are some of the flight test techniques that you use? In our communications before this podcast started, you had talked about a test that you were doing on a business jet where you actually deliberately shut down all the engine-driven hydraulic systems and you were working totally on backup. So what are some of these techniques that you might do?
Currently, I work in civil aviation aircraft certification for the FAA. We look at the systems from the standpoint of intended function and what's it supposed to do, and can it continue to do that under all conceivable circumstances in every part of the flight envelope. If you don't do that with a new aircraft or a product, then you start to ask the customers, the consumers, the operators of the aircraft to be the test pilots. And that's not fair to them to put them in that scenario. So we do some unusual things where we intentionally will shut down a motor and then kill the hydraulic system pump on the other side. We'll just shut that down and use those electric backup hydraulic actuators like I was describing to make sure that the aircraft can still be flown with good flying qualities and handling qualities using the backup system. If you advertise there's a backup system, then the backup system needs to actually work as advertised. So those are the kinds of tests that we'll do. This is how the limits get written in flight manuals. It's usually not at the ultimate capability of the system. It just happens to be the limit to where we tested. So who knows what lives beyond that, but all those limits actually get exercised in real life.
Looking back on your experience flying, as you said, 80 something types of aircraft, are there any particular aircraft that either really favorably impressed you with their flight control systems, or conversely, you saw something in the system that you really didn't like?
Wow. We could talk all day. How much time do we have for this podcast? This is just going to be like an 8-hour podcast now. I'm just going to tell flying stories for the rest of the time.
Not quite 8 hours.
It's not. I think that one of the most fun parts of this job and my career experience has been to fly so many different aircraft. I had a lot of fun with my last active duty Air Force job, which was as the director of operations for the Air Force Test Pilot School. We would bring in weird aircraft for the student test pilots to fly, and we wanted them to see how things shouldn't be so that they could recognize badness in new programs and also see application for the theory that they just got in the classroom. So I had a chance to do that as a student and then also as an instructor. And getting to fly a wide variety of weird aircraft gives you some perspective on where we've been. So I'll tell you, like, as far as like weird flight controls go, I think that looking back at older aircraft, bad example, but functional, got to fly the MiG-15 a couple times, which is a pretty interesting aircraft. It was a privately owned aircraft that we leased, and that is not a supersonic aircraft. This is kind of pre-supersonic age, and getting to see Mach tuck with that aircraft. This is a phenomenon. It's an aerodynamic phenomenon where as you start to approach the speed of sound, you get past about 0.75 or so Mach, your aerodynamic centers start to move backwards on the airfoils. And what that causes is it causes basically a pitch down trim sensation. It causes a sensation that the lift is moved further back, but the center of gravity is still in the same place, and the aircraft just wants to pitch over. Well, going back to early jet age, that's why we thought there was this sound barrier. That was one of those reasons why people thought men weren't meant to fly faster than the speed of sound. Well, it's just an aerodynamic phenomenon, but you can actually sense it when you fly a MiG-15 because it's not optimized to go supersonic. And as you approach that transonic region, then you really sense like the control forces are really increasing nose down. And I'm having to pull back a lot harder, 20, 30, 40 pounds of back force. We had a safety stop. We wouldn't go faster than a certain speed. But that was just one of those things that stuck in my mind is the aerodynamic theory really works and really fun to get to fly an aircraft that our adversaries once flew and engineered. And that was pretty fun. But then on the other side, I got to fly a Fuga, which is a French-made, I think, V-tail single-engine aircraft. And I'll tell you what, that thing was the mixer for the V-tail back in the back, just this mechanical device, but beautiful flying airplane for being kind of from the same age. So that's kind of an example of sort of an interesting, that's not fly-by-wire, but you know, you can appreciate the engineering art in a V-tail mixed single-engine jet aircraft, I guess, too. And so then on the more modern side, aircraft that I just think fly absolutely beautifully. You know, you always love your first one. And the F-16 is truly a magnificent fighter. I've always beaten a Hornet every time I've had a dogfight with a Hornet. So I'll just throw that out there for Jello. But I also got to fly the Hornet too. And the high angle of attack characteristics on the Hornet are unmatched. They're really superb as a fourth gen fighter. So those kind of stand out for me as being really interesting as far as fly-by-wire goes on the more modern side. And then like on the civil side, I worked with civil aircraft certification. So I've gotten to fly some of the new business jets, and I'm just going to put a shout out to Gulfstream because their fly-by-wire systems are pretty impressive and those jets fly beautifully. If you ever get the chance, I highly recommend flying one of the side stick Gulfstreams. They fly beautifully.
Let's talk about what you're currently doing. I mean, aside from your work as a test pilot, you've written a book and you're working on a course, I believe. So could you tell us a little bit about those things?
Yeah, thanks for the opportunity. I get a chance to fly a lot of different airplanes, and I was at a recurrent class for a Gulfstream 650, just going through recurrent with some other pilots, none of whom were test pilots, and always make a point of meeting people and hearing their stories. And I got a call about a year after that class from one of the guys in the course, and he's leading a flight department for a high net worth individual. And they were trying to do as much as they could to be totally grounded and professionals with the systems they're operating. And he said, hey, we're wanting to study up some more on the fly-by-wire system, and we can't find anything outside the flight manual that explains why and how these things are designed. And I know you're a test pilot, and maybe you can send me some information. And I said, oh, yeah, sure. I'm sure that I can find this information easily. As I started to look, and he had also looked, I could only find either aeronautical engineering textbooks, kind of PhD level stuff, or kind of a cartoony YouTube video on fly-by-wire that didn't really explain a lot of the concepts you'd want to know. And really more from a pilot standpoint, not like, how do I build this thing in my garage, but why did they design it that way? What's it trying to do with this alternate control law? Those kinds of things. And so I started writing this down for the guy, and then I kept writing, and it turned into kind of a book. So it's not a very long book, but I wrote a book called Introduction to Fly-by-Wire Flight Control Systems, and it's just meant for pilots who operate these things. And if you're a professional pilot, the day will come when you will operate a fly-by-wire flight control system. It's kind of inevitable for any professional contemporary at this point. But, we get enough to read as pilots, so I didn't want to make just another large book to read. It's actually a pretty short book. There's no math. There's no graphs. It's just like we're sitting at a bar and I'm trying to explain why these things are built the way they're built. So I wrote that. And then kind of in the same vein, I get asked a lot of times, how does flight test work? And what's the point of flight test? And how do you go about that? There's a lot of misconceptions with flight test in terms of the process that leads up to it. It's a lot of analysis. It's a lot of meetings that happen. Really, it's based on just what do we expect the system to do? And I talked a little bit about computer models with you today. And that's the point of flight test. You've got a prediction of what you expect to happen. And then you go fly it and you see if what you flew actually matches the model. And then you change the model as you go and you start from the stuff that's lower risk and you move up into the stuff that's higher risk. So I built a course because I think that that's kind of valuable with a lot of the projects that we see going on today. You and I both had the opportunity, the advantage of getting to work around professional flight test organizations. Being at Edwards was an amazing experience and you get to see some really neat stuff. But a lot of folks that work on developing advanced aerospace systems, they don't get the benefit of that experience before they're thrown into the job. And I thought there's a need to understand some of the vocabulary, some of the concepts. So I built a Flight Test 101 course to try to help explain this. So whether you are a program manager or a young engineer or basically any team member, I think working on a new aerospace system can benefit from this. And so I created something called datalessaero.space. All one word, datalessaero.space. And I'm going to just put it out there as a short course. We'll see if that's benefit for others.
Well, I'm looking forward to the course. I will say I read your book. I give it a 5 stars. And I'll mention to the Fighter Pilot Podcast audience, although it's aimed at professional pilots, I think it would really be of interest to anyone who's an aviation enthusiast and wants a real understanding of how these things work, but isn't necessarily a graduate engineer. And although it's aimed at professional pilots, I think a lot of people who are not professional pilots will also like this book.
Well, I really appreciate you saying that. It's a lot of fun to write a book. It's a little bit of a risk to put something out there, and I really appreciate the positive feedback. So thank you for that.
We normally end interviews on the Fighter Pilot Podcast by asking you how you got your call sign. And, well, first of all, what is your call sign and how'd you get it? If you can tell the story in a family-friendly way.
Yeah, I can. My call sign is Divot, D-I-V-O-T, like on a golf course, a divot. So there's been some other F-16 pilots that have also been named Divot for a different reason. I am not the guy that bailed out and his aircraft impacted a golf course. That's a different Divot. That's not me. I had a pretty severe sports injury when I was in college, when I was at the academy. I actually broke my neck. It's a long story with the medical stuff, but I have some scars around my head and around my cranium, if you will. When I was a younger man, there was a couple spots where hair didn't grow on the back of my noggin. And so that inspired the call sign Divot. Since that time, it's far less noticeable, but at the time, it was definitely a physical imperfection, which was highly noticeable. And that's how fighter squadrons go. I carry the call sign with pride, and I've had it in at least 3 major commands in the Air Force. So I think I'm safe from renaming, but I'll try not to do anything stupid and risk it.
Well, Divot, thank you for sharing your expertise and experience about a truly fascinating topic. Much appreciated.
Hey, Ken, I've really enjoyed talking with you. Keep in touch.
All right, that was awesome, but Divot, my heart aches, man. Come on, how can you pick on me about the F-18? I'm sure you were fighting your fellow test pilots. Clearly, you were never fighting me when you beat an F-18 every time in your Viper. Anyway, apart from the bluster, and yeah, I have been beat up a few times by Viper. I did think that was a very good interview, Ken. And yes, Divot, carrier landings are really cool. I've done a few. But man, right off the bat, Ken, how on earth could a person become a fighter pilot with a broken neck? That just seems crazy.
That is a very fortunate guy. I would think that you'd be permanently grounded after an injury like that.
Well, we've had folks on this show before. One said he was quote unquote slightly colorblind. I think he was, as I recall, back in the 50s. So maybe that was okay. And then we had Cinco, who didn't really want to be a pilot and found his way into it. So I know, again, there's probably people out there complaining, hey, how come I can't get in with a measly little this or that when here's a guy with a broken neck? But man, that is crazy. We should almost have him back to talk more about that. But here's the other thing, Ken. On this show, I'm used to dancing around sensitive subjects. If we're talking about tactics or air-to-air missile capabilities and different things like that. But I was actually surprised how protective you and Divot were about EMP, cyber threats, thrust vectoring. What's the story here?
I look at cyberspace as the fifth domain of warfare. You had land warfare, naval warfare, air warfare. Now we're in outer space. And cyber warfare is really the fifth domain. And I'm going to be as evasive as Divot is. This is just a subject that involves vulnerabilities. It involves some highly capable potential adversaries. It involves countermeasures, and it isn't something I'm comfortable talking about.
Yeah, I guess that makes sense, right? If I was at a convention full of, I don't know, thieves, and I said, hey, the code to my door is this, then I'm more likely to be broken into and have my goods taken. So we try to protect things that are near and dear to us, yeah?
It's something that we have to take very seriously, just as we've always taken things like electronic countermeasures very seriously.
Right.
In terms of security, cybersecurity is the same way.
Sure. Now, there was at one point in the discussion, you talked about maybe something happens and you can push a button and land the airplane. I thought that discussion was actually very apropos because apparently that happened just back on May 10th, I think it was, a Cessna Caravan with 2 passengers coming from the Bahamas to Florida. The 60-year-old-ish pilot passed out and somehow air traffic control talked down the guy who'd never flown before in his life.
Well, the Garmin company, which is in Olathe, Kansas, has a auto land feature for general aviation aircraft, for some of the high-end general aviation aircraft.
Mm-hmm.
But actually, this Cessna Caravan wasn't equipped with that. It was just a question of a cool passenger who got on the radio with air traffic control, and air traffic control kind of coached him, and he landed it. There was no flight control magic here.
We're glad to have a happy ending there, but I think some flight control magic could still be very useful for other people. And I'm guessing that gentleman must have wished for such a feature, but at any rate, he rose to the occasion. Good on him. I hope he takes flight lessons.
Indeed.
But, Ken, with all this talk about complex flight control systems and everything else, I was kind of wanting some basics. For example, your little Archer that you fly, I assume has a horizontal, elevator, and I can't even remember all the controls, right? But an F-18 has an all-moving horizontal stabilator. And then on some of the Grumman products, like the Tomcat and the S3 Viking, they chose spoilers over ailerons. So why are some of the major components chosen the way they are in the first place?
That's a great question. And there's not a simple answer because an aircraft is a very integrated thing. So when you change one thing, it has impacts all throughout the system. But here are a couple of the considerations. One of the considerations is you just have to have adequate control power for the maneuvers that you want to do. So you need to be able to generate the amount of rolling moment or the amount of pitching moment or the amount of yawing moment that you need. Another consideration, how much hydraulic power, or in the case of a smaller airplane, muscle power do you need to move it? If those demands are too high, then you've got another problem. A third consideration is that when you have a control surface that moves, it's reacting back against the thing that's holding it. So let's say you've got big ailerons out on the tips of long flexible wings. If you move those ailerons too far, they're going to twist the whole wing and you're actually going to get control reversal. So you put the stick to the left, it's going to twist the wing to the point where you roll to the right.
Yikes.
So all those considerations go into how you want to have your control set up. So for example, on your F-18, if you had big ailerons out on the tips of the wings, you'd need a very heavy wing to make it stiff enough. So you tend to use, I assume that you get your roll control off for your stabilators also?
As far as I remember, ailerons, stabilators, and a little bit of rudder, depending on what your conditions are when you go to roll.
Right. Probably as you go faster and faster, you use less aileron and more roll-on. Now, as for the all-flying stabilator versus a elevator, it happens to be that Mighty Piper Archer actually uses an all-flying elevator, but it's called a stabilator, not a little elevator at the end of a fixed surface. There's some reasons for that, which have nothing to do with the reason why supersonic aircraft do it. The reason why supersonic aircraft have all flying stabilators is that at supersonic speeds, you get a shock wave that's coming off the stabilator, the leading edge of the stabilator, and it basically means that the elevator, if it was just a little flap at the end, wouldn't provide much value at all. Now, kind of an intermediate case is what I believe you have on your 757, which is that you have an elevator, but then the whole stabilator moves for trim.
Yeah, that's correct.
Right. So there are a lot of different ways of skinning this cat. And similarly, for roll control, you can use differential stabilators, which is, for example, like what a B-1 uses.
Mhm.
You can have spoilers. You can have ailerons. And it's all a question of how it fits into the structure of the airplane and, what's the optimum way to do that. For example, with a B-1 or an F-14, you've got these variable sweep wings. So in some conditions, you just can't move the ailerons because they would bang against the back of the airplane there. So in that case, you really have to use spoilers. There's also a question of redundancy on different kinds of airplanes. If you have multiple surfaces that can, for example, give you a rolling moment, then if some of them don't work, others of them will work, and you can still come home. It's a great question, but it's a very complicated answer.
As are so many things in this business. But you guys also talked about the Ram Air turbines. I flew a military jet with one of those. It was a single engine A4.
Well, in that case, the Ram Air turbine, also called a RAT, you want to have redundancy of power sources, both electrical and hydraulic. It depends on whether the RAT turns one or both. But particularly with a single engine airplane, I don't know the TA-4J that you flew, but it probably only has one engine-driven hydraulic pump and one engine-driven generator. So if those go out, you've got a real big problem, and you got to deploy the RAT to give you that power so you can maintain control of the airplane and start up the engine again.
Yeah. I want to say the A4, man, this has been a long time since I've flown it, but I want to say it had like 4 rats. And if I remember correctly, there was one for electrical, there was one for flight controls. Oh, I can't even remember anymore. But, it was a question of when you had an emergency to remember which one to reach down and pull.
Now, your 757 has a RAT, doesn't it?
Yeah.
So they're used in some military aircraft and some civilian aircraft. When you get into aircraft that have a lot more redundancy, multiple engines and multiple systems driven off of them and emergency power units like you do on an F-16, you tend to less have RATs.
Yeah. Well, my 7.5 has one because it does long overwater crossings, right? So it's a ETOPS concern. ETOPS, I forget what it stands for, but our joke for it is engines turn or people swim. But when I fly to Hawaii, theoretically, I can have an engine fail and still make it back halfway. And then you have a RAT for a little extra redundancy again. So that's kind of scary when you're maybe as far as 3 hours from your nearest divert if you lose an engine. So a RAT's just one more layer there.
Whenever you have a flight control system, except in the simplest airplanes like a Piper Archer, redundancy is a major, major thing.
Yeah.
You've got to be able to fly when things don't work, when things are shot out, if it's a military aircraft. If you take a bird hit, you lose systems. If something jams, you can't lose control of the airplane. That's one of the things that distinguishes transport carrier aircraft or combat aircraft from small general aviation aircraft.
Well, what's this about this course Divot created?
He had a great insight, which is that there are a lot of people who need to know about flight test, but you can't go sending everybody to a test pilot school. It's just too expensive. So he would take some of his knowledge and put it together into an online course, and a fairly low-cost online course that people could take on their own time when it's convenient for them and learn about the basics of flight test. And Divot asked me to take this course. He formed a company called Daedalus Aerospace that does it. And he just asked me to take the course. He wanted to know what my opinion was. It's a really good course. I was emailing back and forth with him. As I said, it's kind of the school solution. It's very much like the way that things are at Air Force Test Pilot School in terms of the philosophy that they teach. But if you want to understand, it's not about flashy maneuvers and this and that. That's what people think flight test is about. It's the various disciplines and how you organize things and how you mitigate risk. And it was a great refresher for me. I really enjoyed it.
Okay. And as we said at the top, he also wrote the book on all this. Where can listeners find the book?
His book is on flight control systems, and it was really oriented towards pilots who understand their airplane and how to fly it, but really want to understand more what happens under the hood without having to get a graduate degree in it. The book is available. There's a link to it on his website, which is kernaerospace.com. That's KERN aerospace.com. It's a fairly easy read, and it's very interesting.
All right. Well, great job again, Ken. Thanks again to Divot. And yeah, I think you've converted me. Importance and sexiness, I think, do combine here in flight controls.
It was a lot of fun. I enjoyed it as always.
Well, then, as we begin to wrap up, I want to thank our newest Patreon strike lead, John Drummond. And of course, as always, the views expressed in this presentation are the personal views of the hosts and our guest, and do not necessarily represent the position of the Department of Defense or its components or contractors. All right, well, that will do it for this week. Ken, thanks as always for another exciting interview about a nerdy but important topic. And I hope you received that compliment in the spirit in which it is intended.
Absolutely. Isn't it great when we can have experts like Divot explain how the airplanes that we all love really work?
Oh, absolutely. Yeah. When folks like him come on and some of the other guests that you've had recently, I hearken back to the we're not worthy. These guys are at a whole different level than me. So it's good stuff. But before you go, you might notice there was about a 12-minute segment that we cut out of your interview, and we did that on purpose. Did you happen to notice?
Yeah, I did. That's the section that Divot describes what he did about in terms of testing the automatic ground collision avoidance system, which I think is one of the most amazing applications of modern flight control technology.
That's right. And we did that because next week's episode features two of our past F-35 guests, and one was involved in a fatal midair collision while flying F-18 Eagle back in 2008. So for you listeners out there, your homework is to stay tuned after the closing bumper and flyby here in just a moment. And we're going to play that 12-minute segment as a primer for episode 148, just 10 short days away. Ken, thanks again for your help today.
Thanks again. It was great.
And for everyone else, take care, be well. Thanks for joining us here on the Fighter Pilot Podcast. We'll see you next time. So long.
You've been listening to the Fighter Pilot Podcast, brought to you by BVR Productions. Got a question for the show? Email us at questions@fighterpilotpodcast.com or leave a message on our listener line at 877-MACH-101. That's 877-622-4101. Be sure to follow us on your favorite social media platform and check out our website, fighterpilotpodcast.com. For exclusive content and to help support the show, check out our Patreon page. Thanks for listening.
Let's talk about one of, I think, the most interesting things that you worked on, which was the automatic collision avoidance system, which is, if you will, a very interesting idea that's enabled by this digital fly-by-wire in a lot of ways. What was it? What did you do on it? What were some of your interesting experiences?
The automatic ground collision avoidance system was really the highlight of my first tour at Edwards. I got to be the project pilot on that as it was still with NASA and was transitioning over to the Air Force side. It's really an impressive system in the sense that it operates full-time in the background, and it tries to keep you from hitting the rocks. It will do so without warning and then give control back to the pilot. So it's the opposite, if you will, of how we normally think of autopilots, where the autopilot does the flying and the human monitors the autopilot and maybe changes which direction it should fly or what altitude, and that's it. But a human monitors the autopilot. Automatic ground collision avoidance system, or Auto-GCAS, as we call it, is the other way around, where the automation monitors the pilot, then will take over without warning, and it's always on. So pretty amazing system. It's already saved. I think we're up to 9 or 10 saves now on the F-16 side. It's implemented with a few differences in the F-22 and F-35, and I think it's going to branch out from there. It's something that could be hosted in just about any fly-by-wire fighter or aircraft. I think one of the most interesting stories from that is getting fighter pilots to not just accept the system, but want the system in their aircraft. I say, as a fighter pilot at heart, I like being the mayor of Cockpit City. I'm in charge, and I fly the aircraft, and I can do it safely. So having an automated system that lives in the background, kind of looking over the pilot's shoulder and might take over, was a challenge to get the fighter pilot community to accept, because it's kind of a little bit of a conflict there. So The secret there, and the reason I think that Auto-GCAS was so successful, is because the priorities for the program was first, do no harm, and then don't interfere. And finally, third was prevent collisions. And that's a little bit of an inversion of the priority order for a lot of other systems that have sought to prevent controlled flight into terrain or other collisions. The first priority was to prevent the collision, and everything after that was sort of secondary. What you see with some of the older systems, which are still very effective, but would not work very well in a fighter environment, things like ground proximity warning system, GPWIS, or traffic collision avoidance system, TCAS. You see those in the civil side, but you get a lot of nuisance warnings, even during normal operations. But anytime you get kind of near the edge of the envelope, you're going to get all kinds of warnings from those systems. They definitely add to safety, but they are not at all compatible with fighter operations. And so for Auto-GCAS to be accepted into the fighter community, it needed to be able to allow basically carefree operations, including low-level operations, 500-foot low level, even down to 200-foot low level, and low-angle strafe, where your minimum altitude is 75 feet with the F-16. And so we had to have a system that could accommodate all of those fairly aggressive maneuvers and not interfere with the operation. The system is not designed to prevent all controlled flight into terrain. They developed that system from the standpoint of looking at safety records and identifying every time there had been a controlled flight into terrain, a CFIT incident with the F-16, and then designing a system that could prevent all of those. And there's a couple of caveats, and those are kind of safety interlocks. So if you put your gear down, you're trying to land, and the system's going to let you land. It will also let you crash if your gear's down, because it's going to be locked out. There's a few other interlocks that are built into the system. But the way that we had to go about getting the community to accept Auto-GCAS was essentially to prove non-nuisance, that it wasn't going to inspire the fighter pilot to look for a way to turn it off because it was giving warnings, or really not warnings. It takes over with essentially no warning. If you get enough of those, then you start looking for a way to turn off the system. And that's what we had to avoid with our development. I could talk for a long time about this, but let me just focus the conversation by saying we had to put this in the hands of some of our operational test fighter pilots at Nellis Air Force Base, get them to fly the system and come back with a smile on their face. That was kind of the graduation exercise for Auto-GCAS, was having some advocates within the operational test community that would advocate for the system and say, yeah, this is going to save lives and it's worth putting into the jet.
I've got several questions about the system. Can the pilot override the system?
Yeah, absolutely. And that's definitely one of the requirements for a high authority automated control system like this, is that ultimately it's you and the robot. And you have to be able to take command. The pilot in command has ultimate responsibility for and authority for operating the aircraft. And if you can't override the robot, then you've violated that sort of fundamental law. So in the case of Auto-GCAS, we call it the paddle switch. It's basically a switch forward of the control stick, and you can simply reach forward with kind of the lower two fingers of your hand and squeeze that, and it's going to stop the fly-up.
When Auto-GCAS does its thing and takes control of the airplane, does it enunciate that to the pilot?
So this was a little bit of a controversial development topic with Auto-GCAS. Yes, it does. And there is, if you've heard me sort of equivocate, there is a little bit of a warning. And there was some debate about whether or not that symbol should be in the heads-up display. The way the system works is it is constantly computing, projecting the future flight path of the aircraft. If you keep doing what you're doing at the speed you're going, the G's you're pulling, the altitude you're at, where are you going to end up? And it has a terrain model for the terrain you're flying over. It's a digital terrain database. It's a more sophisticated digital terrain database than has been previously used in some other systems. It's very high resolution. It was made for use by Auto-GCAS. Essentially, it projects out your flight path, and if your flight path intersects with the terrain, then it's calculating what is your time until impact. and what maneuver would be required to miss. And so when you run out of opportunity to miss, to roll wings level and pull because your time until impact has shortened, you've run out of options and now it's going to do the pull-up. As it approaches that condition, it gives you, it sort of looks like a brake X in the HUD, a big green X that's sort of split down the middle and the two sides come together. And when they touch and it makes the X, it's going to execute the pull-up and it's going to give you a tone, if I remember right. It's been a few years since I did this testing. There was some debate about whether that symbol should come together in the middle because it does give the pilot a very brief but some clue that the fly-up is impending. And there was some discussion in the development team whether or not that should be there, because what if somebody tries to use that to fly nap of the Earth? And obviously the primary way is to look out the front. The terrain clearance heights on Auto-GCAS are so low that trying to fly off that symbol would be extraordinarily high gain. It would be an extremely demanding task, and you're far better just to look out the front of the aircraft. So we were concerned that somebody might try to do that. Ultimately, we left the symbol in, but you only get about, I'm going to say, depending on your rates, you get about a half second of seeing that symbol before it's flying you up. So it's more of a confirmation to the pilot that, yeah, that was warranted. That jet just took over for me, and it got about as close to the terrain as I'm comfortable getting. So I think that's primarily why that was left in.
Does Auto-GCAS use any sensor inputs about the terrain? Does it actually measure the terrain with a radar?
No.
Or is it only operating off of a database?
Well, I believe that there's some validation in strafe with the radar, with the fire control radar. I'd have to look back at my notes. That's going way back. Mostly, the primary way that it is keeping track of where you are and what your time until impact is that very high resolution terrain database, which we actually source that from the shuttle radar topography mission. It's a different data set than a lot of terrain databases will use. It's much higher resolution. And that was one of the challenges as we look to field the system in some other fighters, is it's a massive amount of data. And it's a lot of data that you have to sort through pretty rapidly in terms of what's the terrain out in front of me and just making the calculations based on that slice of the terrain. It's a very large data set, and that made for some challenges as we look to field it in some other fighters. But I will tell you, interesting story. Nobody likes talking about database stories. How is database interesting? But this is kind of an interesting database story. We discovered in the course of developing the system, the legacy terrain database, which is inadequate resolution anyways. We couldn't use it for Auto-GCAS. But we found that some of the errors in that terrain database were due to its source. That terrain database had been provided, it was sort of a geologic survey, and it was intended to model how rainwater and watersheds and water rights were going to end up. That was really the source of that original data. And so they had changed some of the terrain in that database because it wasn't precisely modeling where some of the rivers and streams and water runoff were going. And so they tweaked the model. That was just one of many reasons why we could not use that for Auto-GCAS. But the shuttle radar topography mission was a really great data set. I will say, though, boy, database stories, who thought pilots would want to talk about databases? But there are some anomalies in any database of terrain. Sometimes you get these spikes of, there's not a pole, there's not a mountain there, but it can show up in the database. And so this was kind of interesting as we found some of these errors during testing and even during fielding. There were at least one or two of these that I'm aware of that were found, and they were fixed in that database. There's a lot of ways you try to go and scrub to get rid of those. But I'll tell you, this is probably one of the most interesting lessons learned from that is you can't go and test a information system in a simulation. You have to test it in the real world. Because if you try to go and test something like Auto-GCAS in a simulator, well, your simulated terrain and the visual that the pilot's seeing in the simulator of the terrain come from the same database. And so they totally match up. But that is not necessarily the case for reality, where now the rocks might not be where the database says they should be. And that's a big problem if you're depending on that. So it ended up with a very reliable system. And it's the result of finding some of those lessons learned and anomalies along the way. But no, it doesn't actively measure. It's not a train following radar.